Hi, this is an example problem about the reaction energy of carbon-14 from chapter 32 on nuclear physics. So this gives us a reaction which occurs up in the atmosphere that a neutron is captured by a nitrogen nucleus, and in turn there's a reaction that generates a carbon-14 nucleus plus another unknown nuclear species, which we need to determine in part A. So for part A, the key idea here is that both sides of the equation, and we've got here the reactants, and on the other side we've got the products. Certain things need to have the same value when you sum them up on both sides. So for example, if we look at the mass number, when we add those up, we call this again, the mass number is A. So I'm going to call this R for the reactants. It's going to be 1 plus 14, 15. That means we have 15 total nucleons, which are neutrons and protons. We need to have that same value on the product side. So to calculate what the unknown value of A is, we can say, well, A plus 14 equals 15, and we can see that A is equal to 1. Similarly, we can go ahead and look at the net charge here in the nucleus. So we're looking at the net charge. We're looking at the lower number here is the number of protons. We can see that there's 7 total, right, in the reactants. And so for the products, when we add these up, we're also going to need to get 7. So 6 plus Z equals 7. We see that the unknown Z value here is equal to 1 as well. And if we go ahead and see that Z is 1, there's 1 proton, A is 1, there's only 1 proton, no neutrons, that's just an ordinary hydrogen atom. So if we determine that this guy here, X, A, Z, is actually equal to hydrogen. And of course, if you check that mass, well, that is the mass for hydrogen. All right, so in part B, it tells us, using the given mass values, calculate the Q value of the reaction and state whether it is exothermic or endothermic. So in this case, we're going to be calculating the energy that is released or absorbed in this reaction. Q value is just another way of stating that energy. Now the way we do this is the same way that we always calculate nuclear energies. We look at the difference in the mass between the products and the reactants, and then we convert that mass difference into energy using Einstein's equation. E equals mc squared. So to get Q value, again, this is the energy released or absorbed. We're going to look at the difference in the mass of the reactants minus the mass of the products. We multiply that by c squared, and that converts that change in mass into an energy. And we go reactants minus products because if the reactants have more mass and the products less, then mass has been converted into energy and Q is positive, which is exothermic. On the other hand, if the products have more mass than the reactants, then we had to create mass. The delta M, there's going to be negative, and it's going to be a negative value for the energy, which means that it is endothermic. All right, now when we go ahead and do this, what we need to do is we need to go ahead and add up the masses of all the reactants, and we got to keep all of the digits of precision here. So we're looking at the neutron and the mass of the nitrogen, right? So let me just write this out. Mass of the neutron plus mass of the nitrogen minus mass, in this case we've got the carbon, plus the mass of the hydrogen here. And again, multiplied by c squared. Now when we go ahead and put these numbers in here, Let me pause it for a second, and then I'll just write them all down. All right, so I've written down all the masses, and I've been careful to put all the correct decimal places there. These are all in units of U, AMU. Now, when you're working on problems here and you need to look up masses, let's say, what you're going to need to do is go and look those up in the book, because sometimes when you see these masses on the internet or something, they might be slightly different, and that could cause you to be off slightly by rounding. I've gone ahead and taken this appendix from the book, Appendix F, which you can view through Wiley Plus Read Study Practice, or I've made this available in the module for this week, so you can go ahead and just look things up, like here's hydrogen, there's the atomic mass. For example, go down here, you can look and see which carbon isotope you want to do, carbon-14, there it is. And so we just get the masses from that data. All right, now again, be really careful when you calculate this so that you get the answer right here with all the decimal places. I ended up getting this to be 0.0000673 U times c squared. And now at this point, all we're going to do is do a conversion straight to MeV. So we've got this conversion factor here. 1U is equal to 1U of mass equal to 931.5 MeV per c squared, other units of mass. So we're going to go ahead and use that conversion here. I want to get rid of the U's, put those in the bottom. And then that's going to be 931.5 mega electron volts per c squared. We're going to cancel out the c squared, which is nice, those are gone, and we're going to cancel out the U, and we are left with an energy in mega electron volts. Putting that number into the calculator, we get a value of 0.626 MeV. Now, that's a positive number. That means the reactants had more mass than the product, so some mass of the reactants was converted into energy, and that is positive. That is energy released in the reaction. We say that that is an exothermic reaction when energy is released. And in fact, that is how carbon-14 gets generated in the environment, and when organisms respire that oxygen, they're able to incorporate that carbon-14 into their bodies at this same rate that is present in the atmosphere. Of course, once that organism dies and stops respiring the carbon-14, it begins to decay, and this is how we use carbon-14 to detect the age of an organism as the decay has occurred, ever since it first died.